A modern X-ray machine maps the internal structures of the human body in milliseconds, translating high-voltage electricity into clear anatomical data. But beneath that speed lies a massive thermodynamic flaw. For every burst of electrical power fed into an active X-ray tube, 99% of that energy is wasted as intense, destructive heat. Only about 1% is actually converted into the diagnostic X-rays used for imaging. The process starts at the cathode. A large electrical current heats up a coiled tungsten wire until it reaches temperatures high enough to literally boil off a dense cloud of electrons, a process known as thermionic emission. Once that electron cloud forms, a massive voltage is applied across the tube. In a gap of just 1 centimeter across a total vacuum, those negatively charged electrons are catapulted toward a solid metallic barrier at roughly half the speed of light. As this diagram shows, to understand the power of this collision, we have to look at the kinetic energy equation. An electron's mass never changes, so to increase the penetrating power of an X-ray beam, the operator increases the voltage, which drives up the velocity. By doubling the speed of the projectile, the resulting kinetic energy actually quadruples. When trillions of these hyper-accelerated electrons suddenly slam into a solid metal wall, their massive kinetic energy has to go somewhere. The friction from this subatomic crash generates enough thermal energy to melt steel. To see exactly how we extract that vital 1% of diagnostic light from the collision, we have to zoom down into the atomic structure of the target itself. The first way we produce X-rays is through characteristic radiation. Here, an incoming projectile electron strikes with enough force that it completely ejects an inner K-shell electron right out of the target atom. This collision creates an unstable void. An outer shell electron instantly drops down to fill that gap. When it does, it sheds the exact difference in its binding energy as a highly specific, discrete X-ray photon. The second, much more common interaction is called Bremsstrahlung, or braking radiation. In this scenario, the incoming electron bypasses the orbital shells entirely and flies dangerously close to the atom's heavily positive nucleus. The intense electrostatic pull of the nucleus acts like a gravitational slingshot. It forces the passing electron to rapidly swerve and decelerate. The kinetic energy lost during this braking maneuver is immediately cast off as a broad, continuous spectrum of X-ray light. These two microscopic braking phenomena forge our medical images, but the remaining 99% of the kinetic energy absorbed by the target atoms simply vibrates their outer electron shells, leaving behind overwhelming localized heat. Containing that much thermal fury inside a sealed glass tube poses an immediate problem, keeping the physical hardware from burning to the ground. The first line of defense is the choice of metal. The target is alloyed with tungsten, which has a dense atomic number to maximize X-ray production and an incredibly high melting point of 3,400 degrees Celsius. But of course, even tungsten has its limits. If millions of high-speed electrons continuously bombarded one stationary pinpoint for an entire exposure, the metal would pit, crack, and vaporize. To solve this, engineers introduced a mechanical workaround, the rotating anode. Inside the vacuum tube, a heavy metallic disc is mounted on a shaft, spinning at over 3,600 revolutions per minute during an exposure. By continuously rotating the target, the intense electron bombardment is distributed along a large circular track on the face of the disc. This allows the heat to spread out safely into the surrounding metal, saving the machine from melting itself. This spinning disc solves the melting issue, but it creates a geometric conflict. A massive impact area is great for heat distribution, but projecting a large beam creates a blurry, useless medical image. For a sharp picture, you need a tiny focal spot. The line focus principle solves this. The anode is tilted between 12 and 17 degrees. The incoming electron beam strikes a wide, elongated area, ensuring maximum thermal distribution. However, this angled geometry physically compresses the downward projecting X-rays into a tightly packed, effective focal spot. This slanted geometry bypasses the physical limits of the material. It provides the heat-shielding benefits of a wide crash site without sacrificing the visual sharpness of a pinpoint beam. The tilted anode handles the heat, but it leaves behind a physical quirk in the output beam known as the anode heel effect. Because X-rays are produced slightly below the surface of the anode,
The photons exiting the lower, thicker edge, the heel, have to push through more solid tungsten than the photons exiting the upper edge. This material absorbs energy, making the radiation beam slightly weaker on the anode side. Radiographers actively exploit this uneven beam when positioning a patient. By placing thicker or denser body parts, like the lower spine, under the stronger cathode side of the tube, they use the gradient to produce a perfectly even exposure. From the console, the operator maintains total command over the physics. They can dial in the exact number of electrons being boiled off, known as the MA, and independently adjust the acceleration speed, or kVp, to shape the final penetrating power of the beam. Every successful scan relies on this precision physics engine, which pushes tungsten to absolute limits of its melting point, just to yield a clear window through the human body.